And on the front slide here is our first aircraft, which is going to be flying this summer, called Protium. It is a pre-existing aircraft, but we were modifying it to be able to fly off of hydrogen as fuel through a fuel cell. I won't go too much on my background, except that I will say that my program, or my whole career, has primarily been in the space program. And when you develop new technologies for the space program, they're inherently being designed for extreme environments, whether that's the launch vehicle environment getting out of Earth's gravity well, or whether that's the extreme reentry heating loads that you see when you enter a planetary body with an atmosphere. And as a result, your engineering design principles are focused on doing very difficult things, doing them right the first time, and doing them very mass efficiently and power efficiently. Maybe not cost efficiently. Everybody knows the space program does cost a lot of money. But of course, when you bring that kind of mindset here to Earth, you can also solve complex challenges. But you also have to add in the third dimension of cost efficiency, because any commercial venture has to be affordable. But my background is as an engineer. All of my degrees are in aerospace engineering, but I'm also a commercial pilot. So I have very much a love of aviation, of flying in small planes, and doing emergency response and disaster relief in the context of using small planes. So aviation has many positives to our society outside of CO2 emissions, and that's what I want to target, is reducing those CO2 emissions from aviation. Did I do something there? Or did it get kicked off? Okay. So what I will talk about is, because the motivation for my company is to bring about technology to mitigate climate change for aircraft, which is one of the most difficult things to decarbonize. And naturally, that will help a lot of other sectors, such as mobile energy transport, heavy-duty ground vehicle transport, and marine transport. And when we talk about technologies that are being developed today, we do always think about the CO2 aspect. And the space program has received a lot of criticism, rightfully so, over the past 5 to 7 years or so, as there's been a push for commercialization of space and, I would say, tourism in space, right? And so these are some examples of, Blue Origin, which is now sending very wealthy people into space. And obviously there is a carbon footprint associated with it, even though it's hydrogen, because it's gray hydrogen they're using. And we do have to think about, when we have all these new technologies coming up, whether it's space travel, whether it's AI and ChatGPT, we do have to think about the environmental cost, the societal cost behind what we're doing. And are we developing technologies because we need to, or just because we want to? And I would argue, with the state of climate change, we probably should be developing things because we need to. But I will say that I do take most of my inspiration from the space program. I became an engineer because as a small child, I watched science fiction with my dad, and I knew that I wanted to be an engineer to facilitate the exploration of space. One of my heroes growing up was William Shatner, who's Captain Kirk from the original Star Trek, and I got to meet him during the pandemic, actually, because he had a new TV show where he was interviewing experts, and so he interviewed me, and I was kind of like, oh, but I was able to have a good interview with him, and it's online if you're curious, watch it. But he is just like his character, is what I'll say, if any of you know Star Trek. But I am absolutely motivated by science fiction. And the irony is that many technologies that we see today, whether it's from our cell phones, which used to be flip phones, which used to be the Star Trek communicator, to vehicles such as the Hyperloop, which I worked on for a couple of years, to space travel, to vertical takeoff and landing aircraft, all kind of have their origins from an inspirational perspective in science fiction. So as an engineer, software engineer or hardware engineer, you could make science fiction a reality, which I think is kind of exciting, and I've always loved that personally. And what that means is that together, as technologists, as engineers, as computer scientists, we can build the future as we imagine it to be. That's a really powerful tool that we have in our hands because of our training as technical people. And one of my favorite quotes, actually, is to describe the difference between science and engineering, which is that science is about making observations, whereas engineers basically are creating this future world, things that have never existed before. And I think what we see during the pandemic is that we had massive improvements in medical science in regards to mRNA vaccines, which enabled rapid distribution of vaccine technology on a really short time scale. That same technology technology is now being implemented for things like, different cancer treatments. So one of my other favorite sci-fi books and movies is The Martian, where this guy, astronaut, gets stuck on Mars, everyone leaves him behind, and he's able to science the shit out of it and get his way back home to Earth. And I think there's a lot of truth to that. We even saw that over the past couple of years. But I kept on showing you images of utopian science fiction, which is Star Trek. There's also dystopian science fiction like Blade Runner, the old one, as well as the new one, Blade Runner 2049. And what this is a representation of a future Los Angeles, which is where I live and where my company's based, where basically climate change has run amok. All of the air quality is terribly polluted. All the animals are gone. So for any of you who've actually read Philip K. Dick's book, Android's Dream of Electric Sheep, which was the inspiration for the first Blade Runner, all the animals are gone. The whole android sheep is because people still wanted to have animals around, so they made android versions of those animals. But if you've ever been in California during a forest fire, it actually does look like this. So we're not too far away, unfortunately, from this reality. And only just this past summer, the northeast of the United States, roughly where New York is, also experienced kind of its first forest fire and saw climates like this. So climate change, unfortunately, is very real, and it affects our air quality, it affects our health, and it actually disproportionately affects people who are lower income and in developing countries, which is really sad. So although the sci-fi engineer can do really cool things, we always have to think about the environmental cost of what we do. We absolutely have to going forward. And even that has a relationship to the space program. So these 3 planets, in case you don't know, Earth is our home in the middle. The one on the left-hand side is Venus, which is 1 planet in from us. The one on the right-hand side is Mars, which is 1 planet out from us. Planetary scientists believe, at the formation of the solar system, these planets were all relatively similar to each other. But now, Venus has a surface temperature of around 470 degrees centigrade and 100 atmospheres of pressure. Mars, on the other hand, has a surface pressure about 1% of what it is in an Earth, not a vacuum, but almost, and primarily CO2. So these 2 planetary bodies experienced planetary-level climate change. And although we think we have an idea why that happened on Mars, there was an asteroidal impact that shattered its molten core, disrupted the magnetic field, ripped away the atmosphere. What we believe happened on Venus, however, is a runaway greenhouse gas effect, which resulted in its oceans boiling, a really thick atmosphere, getting hotter and hotter and hotter to the state that we have today. So one of the reasons for Venus exploration is to actually understand climate change at the planetary scale and look for analogs to Earth, which I think is really interesting and disturbing, because we certainly don't want to go that way. But now let's take it back to home, back to Earth, back to our anthropogenic sources of CO2 emissions. That means what human society, people create. And unfortunately, there's a lot of emissions from the transportation sector. When you look at emissions from the transportation sector in terms of the different ways that you move around, ground vehicles such as small cars account for about 40%, heavy-duty vehicles such as trucks count for 34%, and then aviation counts for 11%, and marine counts for 11%. So obviously, ground transportation is the bulk of those CO2 emissions, and the good news is that with ground transportation, it's actually easier to electrify it, it's easier to decarbonize it because you can run directly off of the grid. Aviation, very difficult, right? Because you can't run off of a grid and batteries are too heavy. I'll talk about that. Marine, once again, another challenge where you have to carry the energy storage with you, and if you're carrying lots and lots of payload, batteries are probably not your solution either. So we think, have a good solution for ground transport, probably eliminating most cars, shifting over to mass transportation, which you have a fantastic version of that, obviously, in the Netherlands. So get all that on the grid, on a catenary. Then you're left with heavy-duty ground vehicles, aviation, and marine. And that's kind of where my company comes in to pick up that space. And this other graphic here shows you the CO2 emissions and other types of greenhouse gas emissions from different forms of transit. And I think the most interesting thing on this graphic is that it's all about utilization. If you do have a transoceanic flight and it's packed to capacity, then this per passenger CO2 output is more reasonable. If you're driving around in an SUV with 1 person, like we see a lot of in the Midwest of the United States, not a very good use, right? Very high CO2 per passenger kilometer. But ultimately, if we get away from CO2 emissions, then we can get rid of our carbon footprint. So what we really have to think about is reinventing ourselves and reinventing transportation. And we have to think about the systems engineering principles of how one reinvents any engineering system. Obviously, accessibility is incredibly important. If everybody can't have access to it, why are we doing it, right? It doesn't solve the public transportation problem. Has to be safe. No one's going to get on a form of transportation which is unsafe, perhaps other than people who do, sadly, submersible risky activities. Cost is a really important one, right? If it isn't affordable, the developing world can't afford it. Lower income people can't afford it. Only the top 10% can afford it, and that is not a good solution either. It has to be interoperable. Amsterdam, one of the best places probably with regards to interoperability of transportation, going from the airport to the train, to the tram, to a bicycle. That's super important for any form of transportation system. And environmental impact, of course, that is the #1 challenge of the day, which is mitigating our carbon footprint and becoming more sustainable. So when we think about transportation, we always have to think about energy. Where are we getting our energy from that we're going to convert into this mechanical motion going forward? And when we think about emission-free energy, when we think about green energy, we always have to think about green electricity, and we have to have a way to store that green electricity. You can create green electricity using solar and wind. Europe has a huge amount of wind. I don't know how much solar it has. The United States has a tremendous amount of solar, right? So we can generate tons and tons of electricity from the most wonderful nuclear power source there is in our solar system, our sun, right? It's only undergoing nuclear fission itself. And then we have to convert that into a way that we can store it in a vehicle application. And that could be done with hydrogen and fuel cells, which is what we're working on. It can be done with batteries. Some people also make the argument of doing hybrid systems where you simply still burn gasoline and you use an electric motor because it's more efficient. I think that's a in-between solution for some things, which is good, but probably not a solution for aviation and not a solution for any kind of industrial or home energy use. And this is just a great example of a solar concentrator facility that we have being developed where we're based up in California in the desert region, where instead of just putting on a solar panel, you collect it on mirrors, and those mirrors are actually actuating with artificial intelligence to align them to give you maximum transference of the radiation from the sun to a column of molten salts, which then basically gets heated up, makes a gas, turns a turbine, and makes electricity. And so this is actually a more efficient way of harnessing solar energy and also consumes less footprint on the ground, which can be great for island countries and anybody who's got, space limitations. But what I like to come back to when I talk about the source of energy, our primary source of energy in our solar system for all of us is our sun, and our sun is made of hydrogen. All of space is made of hydrogen, right? It's primarily a vacuum, but hydrogen is the most abundant element in the universe. It is by definition the most renewable source of energy we could possibly find. So it makes sense to use that. And many people don't know this, but the word hydrogen actually is from Greek, which means hydrogen, which means basically genesis of water, right? Hydrogenesis. And so you can use a process called electrolysis to make hydrogen, which means taking the water molecule, H2O, putting electricity into it, splitting it up, and then generating clean hydrogen and clean oxygen if your electricity comes from a green energy source. And so electrolysis is the way that everyone is shifting now to be able to generate hydrogen here on the ground. It also can be used in space because fuel cells have as a byproduct water, so you can re-electrolyze that water to generate hydrogen and oxygen for your fuel cell in space. And that's exactly how NASA originally developed proton exchange membrane low temperature fuel cells for the space program. Back in the Apollo era, as well as the space shuttle, they used hydrogen fuel cells as energy storage because they were incredibly efficient and give you excellent energy density, excellent power density. And so I always like to take it back to, there's a lot of inspiration that comes from the space program. There's a lot of really fantastic technologies that were developed by the space program that eventually do make their way down to Earth and give us an amazing, technology to use for our own terrestrial use cases. And although it did cost them money to develop this, that was research money that was paid in the past generations. It was a return on investment, you can look at it as, for using it on the ground today. And so Sometimes people ask me when I do these events, well, hydrogen fuel cells, they may be on spacecraft, but when are we actually going to have access to them? Well, we already do. I actually own a hydrogen fuel cell car. This is my car. There's 3 of them that you can buy in California. Sadly, only in California because we have infrastructure for it. There's one from like 2 Japanese manufacturers and then 1 Korean manufacturer. And it works really well. There's a button on the dashboard that says H2O. When you push it, your car releases water. It's releasing water all the time because that's the output of the reaction, but it has a cache of water so that if you didn't want to release it, let's say, I don't know, on the street, but you wanted to release it on your driveway, then you can choose to do that. And that water is actually completely clear, it's distilled, and it has filtered even particulates out of the atmosphere. So I guess my point here is that this is technology which has its birth in the space program, but is real, is in use, and is a great solution to electric vehicle ground transport, as well as what I'll be talking about, air transport. And I think that's a really cool thing because it's not, always 10 years away. It's here today. So I actually took this graphic from a European Union report on hydrogen technologies and hydrogen fuel cells. And the big push in Europe, the big push all over the world is green hydrogen. And as I mentioned before, green hydrogen means it's produced by green electricity. Meaning it goes into an electrolyzer, the hydrogen is produced, it's stored, and then it's made available to a variety of industries. The challenge today, however, is there is not enough electricity to produce the amount of hydrogen which is required even for the manufacturing sector. And that's the reason why the bulk of hydrogen still in use today is something called gray hydrogen, which is hydrogen which is produced from CO2 reforming. But I like to see the positives of the situation, which is that we know that we want to produce more hydrogen. If we produce more green electricity, we produce more hydrogen. If we produce more green electricity, we produce more green electricity for everything else too, right? So it's synergistic. So it's a way to really kind of find synergies between energy production as well as energy storage, as well as energy end use, which is all helping each other for us to be more carbon neutral. And I have another graphic which talks to you kind of about the energy space, but there is always a challenge, and the challenge usually does come down to cost. And right now, green hydrogen is more expensive than gray hydrogen. So the industrial sector is still getting their hydrogen from gray sources, but I am happy to report that in California, specifically Southern California, when we go to our hydrogen fueling station, it actually, on the website, it tells you what percentage the hydrogen is green, and for us in LA, it's 100% green. So there is enough being produced locally in the Southern California area to be able to support hydrogen for our vehicles, which is 100% green, right? So this is great, and it works really well because we're in a really sunny area, tons of solar. It obviously wouldn't work so well in parts of the world and parts of the country where they don't have a green, electricity infrastructure. So that has to be developed across the planet. Blue hydrogen, just as an aside, is gray hydrogen coupled to carbon capture technology so that you remove carbon that you're putting out in the process. I don't think that's a good long-term solution. I think the real long-term solution is to shift entirely over to green hydrogen because it gives us a more sustainable electricity grid to begin with. So now I'll shift over to talking about why hydrogen, and the answer comes once again from rocket science. Comes from my first job as an engineer right out of college, which was working on the development of launch vehicles, specifically cryogenic launch vehicles for Boeing. And the propellants of choice, the propellant and oxidizer combination of choice for launch vehicles is liquid hydrogen and liquid oxygen because it has the highest energy density of any chemical propellant combination on Earth because hydrogen weighs so little. There's a lot of energy associated with it and it doesn't weigh a lot. So in this graphic, what you can see here is that hydrogen has an energy density, megajoules per kilogram, 3 times that of jet fuel. That's really significant, right? That means you can have the same amount of stored energy, but you weigh 1/3 the weight. So that's a huge boon for aviation, obviously, and it's a huge boon for any industrial use. Anything for moving around commercial applications. Now, there's another side to this, which is that hydrogen doesn't have to be mined in Russia, in the Middle East. It can be produced in your own backyard. And the hydrogen infrastructure in Europe is about actually creating it locally and using it locally, so you don't have to pay a CO2 footprint to move it around. So not only is it emission-free, carbon emission-free, but it also is renewable in the sense that it comes from water, which is a renewable resource. And it's locally produced. So these are some of the real advantages of shifting over to a clean hydrogen energy economy. Now, when we think about this in terms of transportation use cases, once again, this graphic is from this great European Union report that I took. This is a function of the weight of the vehicle and the daily range that needs to be traveled. This basically tells you the amount of energy which is required. And you can see that all those small cars are kind of down here on the left-hand side, which is where current hydrogen and fuel cell technology has been designed for. There's this great synergy between railway, big buses and trucks and airplanes and ships at this energy space. There is no technology that's being developed for this group of people. They're simply repurposing car technology, which obviously is for a very different purpose. So hence the reason why I started my company was there was a huge opportunity there that needed to be worked on. But anybody who's an entrepreneur out there, or who anybody is going to become an entrepreneur, and I suggest you do, you're going to face a lot of opposition, unfortunately, from the status quo, from the people who always do things the way they've done them. And I was told, oh, why are you going to develop hydrogen fuel cell technology? It's so complicated. No one's going to buy it. Hydrogen's never going to be there. But sometimes in life, you have to do the difficult things because no one else is going to do it but you. If it's your passion to solve this problem, then you need to do it. So I take, again, my inspiration from the space program, the Apollo era, is we go to the moon and we do these things, not because they're easy, but because they're hard. And in the case here, it may be hard, but we have to do it, right? Because we have to protect our planet, because we see that climate change is happening. So that's kind of segues into my little video that we made for my company last year. So hopefully it works.
I'm Dr. Anita Sengupta, professor of astronautics and founder of Hydroplane. After nearly 2 decades of working on complex space technologies like the entry, descent, and landing system for the Mars Curiosity rover and developing ion propulsion for deep space exploration for NASA, I founded Hydroplane to develop advanced technologies to decarbonize aviation. At Hydroplane, a team of expert engineers and scientists is solving this problem by developing and building a 200-kilowatt hydrogen fuel cell power plant for the aviation industry. Hydroplane's innovative approach of stacked modular fuel cells allows for easily scalable solutions from single-engine aircraft to helicopters, eVTOL platforms, and regional aircraft. In our agile workflow, we use off-the-shelf components where possible and develop new technologies and systems where necessary. Our novel approach will lead to significant improvement in efficiency and a substantial weight reduction, making us an emission-free alternative to piston and turbine engine power plants for aviation. Hydroplane's innovative fuel cell power plant will provide over 300 miles of range with no charge time, no battery replacements, a low noise profile, while only emitting water. You can be part of a cleaner future. Join us as Hydroplane develops the world's first single-engine aircraft hydrogen fuel cell power plant.
Okay, so what hydrogen fuel cell technology coupled to electric motor technology gives you is an electric propulsion system for any type of vehicle. Obviously, we're doing it coupled to an electric motor, turning a prop for aviation, but it can be used for trucks. And it can also be used for marine motors, off-board motors, for example. Now, the advantages, as I kind of already mentioned in that short video, is that it is carbon emission free. Anybody who has an electric vehicle knows that the noise of an internal combustion engine compared to just, if there is an electric air compressor even inside your hydrogen fuel cell car, it's super quiet. So that is another environmental benefit, is a reduction in noise signature for aircraft and people who live in the vicinity of flight paths of aircraft. That's important. Now, if you have an electric vehicle, you know that your maintenance costs basically go to zero because you're no longer doing oil changes. You're no longer getting wear mechanisms associated with the high temperatures and pressures inside of an internal combustion engine. And ultimately, what that leads to an aircraft owner and operator, or to a trucking fleet owner and operator, or a bus fleet owner and operator, is lower operations costs. So when you're trying to make a commercial justification for a new technology that mitigates climate change, if you can also tell people, and it will cost you less money, people will buy it, right? It is the right engineering solution. Going back to that little graphic I had before of how you reinvent a transportation system. In the context of electric flight, it depends upon the size of the aircraft. The smaller the aircraft, the smaller the amount of people or payload that you're carrying, the lower the maximum power requirements are. So technically, technically, we already do have electric flight with drones, but they typically only carry, 5 kilograms of payload, and they fly for really short times and really short distances. The next use case for aviation is general aviation, single-engine aircraft, which is used for flight training. It's used for air taxis, offshore transport, and it's also used for emergency response and disaster relief. I'm also a pilot with the Civil Air Patrol, where we do disaster relief missions, and we use single-engine aircraft because they're very mobile. You can fly them low to the ground, and you can do more interesting things on shorter runways. Emergency response, also, if you have helicopters to get people, across from point A to point B when they've been injured, or to drop off supplies for a war-torn area or a disaster area. There's a whole new industry, which you can debate whether or not it's real or not, urban air mobility, but that also is already focused on electric aviation, but they can only fly for a couple of minutes because batteries are so heavy. And then the goal, of course, is to get to cargo and regional transport, and this technology is evolutionary, but we're talking hundreds of kilowatts over here, and then we're talking to a couple of megawatts for the cargo and regional transport case. So you got to start at hundreds of kilowatts level and make your way up to the megawatts level to be able to get certified and regulated and into flight as quickly as possible. At least that is my rationale behind how we're operating the company. And this graphic is a great one. This is a graphic of volumetric density and gravimetric density. So 0 clearly is not where you want to be. Lithium-ion battery is the worst solution to energy storage, both volumetrically and in terms of mass. Hydrogen, very difficult volumetric one for sure. We can talk about that, and I'll show you some of the technologies that we're developing on that front. But from a gravimetric energy density perspective, it is the best solution out there. You can kind of see how diesel and gasoline are great on the volumetric and good on the gravimetric, but ultimately, if we're going to invest all of our money as a society in electrification on lithium-ion batteries, that is pretty dumb, right? Because it is not very useful from this perspective, and it's a kind of a showstopper for heavy-duty transport and for aviation. And another graphic that we created is to show you, as you go up in total cruise time, which is you want to fly longer, you want to store more energy, you start to see the real benefits of using both liquid hydrogen as well as using fuel cell technology over batteries. You want to fly long on a battery, you have to carry more batteries. You want to fly longer on a fuel cell, you have to carry more fuel. But fuel is a really efficient way to store your energy versus batteries, which are very heavy. So you pay up front for the weight of the fuel cell based off of your peak power, and you store the rest of your energy in the form of fuel, which is in the form of hydrogen. So that's kind of the logic behind it. Now, I will say what we're doing specifically is a hydrogen fuel cell at the 200 kilowatt power point, which is 270 horsepower, modular up to 1 megawatt, which supports a range of aviation use cases today. And because the aircraft are smaller, it's easier to get them certified, right? Jumping on your next Ryanair flight or your next KLM flight on a twin turboprop with hydrogen, which has been certified, unfortunately, is at least 10 years away just because of the regulatory space. This is a way we can start flying very, very soon, as in less than 2 years, which was the goal. And in engineering, when you develop a product for one use case and you modify it to a slightly larger use case, it's easier to do that certification upstep than is to do it from scratch. It's something much larger. So I've already talked about the other advantages below previously. So I wanted to talk to you a little bit about hydrogen fuel cell technology works and kind of why I'm so passionate about it as an engineer. It's an entirely passive system. It doesn't have any moving parts. It operates at a relatively low temperature, 70 degrees C versus hundreds of degrees C, 1 atmosphere versus many, many atmospheres. And what that means from an engineering perspective is it doesn't really wear at all, right, as you compare it to an internal combustion engine process. You have hydrogen gas going into the anode, which is in a gaseous form. Even if you store it as a liquid, you still turn it into a gas. The hydrogen gas is H2 molecule, is disassociated when exposed to a catalyst material, which then forms hydrogen ions. Those hydrogen ions pass through a membrane, which is your electrolyte. The electrons released in that dissociation process is your source of electricity. The hydrogen ions then recombine with oxygen from the air, which also is split up using a catalyst, and the hydrogen plus the oxygen forms water. It's the reverse electrolysis reaction, and water just comes right out of your fuel cell. So you require an upstream source of hydrogen pressure, an upstream source of oxygen pressure, which is the air, and then naturally they'll go through these channels, and they conduct this reaction, they produce electricity, and out comes water. And it is a very passive system for that reason. So 0 moving parts, which from an engineering solution is always a really positive thing. So this, of course, was developed, the membrane technology, back in the 1960s for the space program. And there's been many versions of the membrane technology that have been proved over time. And we're working on a new membrane ourselves. That's one of the contracts that we have with the Agility Prime program, which is part of the Air Force. And in the interest of time, I'm probably not going to show this video. Maybe I'll just go through it really quickly. So just to show you, in the core of the fuel cell is a membrane. It's called a polymer exchange membrane. That membrane is literally fabricated in a laboratory environment. Obviously, in the industrial scale, this will be done by robotic equipment, not by people. So the membrane is being formed here along this thin layer. So the height of that thing is set to make the membrane thickness that you want. That material is like a solution, which then goes into an oven. It's cooked in the oven, and out pops a membrane. So there's obviously time at temperature associated with this, but it's a little bit like an easy bake oven, which is what I describe in the United States. It may not have an analog here in the Netherlands. So out pops a membrane, which will show up. It looks like a piece of saran wrap. So for our fuel cell, the membrane is actually much bigger. This is an experimental one we have. And this is the membrane that goes in individual fuel cell, multiple fuel cells, putting out around 1 volt, go into a fuel cell stack. That's an individual cell. Our fuel cell stack is obviously a lot bigger. But that's kind of like the core behind what is going on. And what we're doing is optimizing the fuel cell in order to make it more cost effective, more weight efficient, and more durable for the aviation use case. So our design that we developed over the course of the past 18 months to be integrated onto a single engine aircraft. You can see our power plant on the lower image here. It's taking as a drop-in replacement to the existing engine in the front of the aircraft, works with a Piper aircraft, works with a Cirrus aircraft and a Cessna aircraft, and then we have wing-borne liquid hydrogen tanks to allow us to have the same range, which is typically expected by this type of platform. I will say that there are some unique challenges to fuel cell technology for transportation use cases because they do dissipate heat. It's not high heat, but it's heat that you have to get out of the systems. You do have to have a more aggressive thermal management system. So instead of using air cooling, you have to use liquid cooling. And that also is not a engineering marvel. That's something which is done in many different industries, but it's different than what you would normally have in an aircraft, for example. And so one of the big things that I found as a challenge as an entrepreneur is that nobody works in this field, right? You might find a few people in Japan that work in Japan on fuel cell technology. You might find PhD students who work on individual single cell fuel cells, but nobody works on fuel cell stacks. So it was actually really hard for us to find a team of people who could actually do what had to be done, but we were able to because of the interdisciplinary nature of my background, as well as me having a pretty big network that I could find people to pull it into different areas, and people who were just really willing to try and do difficult things. But as I've seen from the space program, you're never going to find somebody who's landed on Mars before, so you kind of have to engineer it yourself. But it's been really cool because we have both vocational employees who are automotive technicians and aviation technicians and electricians, as well as engineers who are aerospace engineers, mechanical engineers, and electrical engineers, as well as pilots. So many on the team are also pilots. So our next stage of the company is our flight demonstration of our Protium aircraft. We are based in Los Angeles. Our aircraft is based in the Los Angeles desert north of the main city. Nice flat area that you can do lots of experimental flight test programs. We're actually funded by the Air Force as well for this development. So our end-use customer is Edwards Air Force Base, who is kind of the the test center of the United States when it comes to new aircraft developments for both civilian and commercial purposes. We had a big milestone in October of last year. We finally got our own facility. So this was it before we moved in. This is it now. It's not huge. It's 2,000 square feet, which is actually pretty big from my perspective. But it was, as a startup, when you have your own space, you start to make rapid progress. When you try and work in other people's spaces and find like seats to sit in, it doesn't work out well. I learned that the hard way. So as soon as we got our own space, we just started accelerating our activity level. We also ran into some challenges in using shared space because we have to take in hydrogen. So this is us now. We've been doing iron bird testing of our power plant for the past 4 months. We have our own machine shop as well. So we actually went off and bought all the machine shop equipment because that was way cheaper than paying other people to do it for you. So in-house assembly, fabrication, prototyping, that's another way in which startups can be really cost effective. And this is the power plant, which is currently installed in the aircraft. And so it looks like a rat's nest of parts because it is. There's a combination of airlines, hydrogen hydrogen lines, coolant lines, electrical cables, high voltage, low voltage, but this is everything that we built up in the lab. We made sure it worked right in the lab before we put it into the airplane. And this was not our last test, but one of our last tests. And of course, we are dealing with high voltage, 300 to 500 volts, which is why you have to wear big gloves and things like that. And we're really proud of our electric air compressor, which comes from a European country, by the way, developed for Formula One applications. So I'm going to give you a short set of videos. This is our hangar location out in the desert. It's really cool. We have access to a shared space in the local college's hangar where the college we have an intern program with, so we actually are training students on how to build and test electric aircraft. We've removed the internal combustion engine for aircraft and replaced it with all of our own hardware, including our engine compartment box, which houses the fuel cell and all of its balance of plant technologies. All of that designed and built and tested by us. I think I just showed you this one. Here, okay, so this was the first time when we actually brought the fuel cell to the hangar, and so we were coming up with ways to be able to install it into the aircraft, so we decided to use a cherry picker, which is you bring it from the top and bring it on down. And I think this was me videoing it from the top of the aircraft. This is the first time that we had the team actually bolting it to the engine compartment structure. And one of the approaches that you have is that you want to leave the primary structure of the aircraft as is and only bolt to it because it helps you with the certification process. So that drove our entire design so that we could eventually sell it to aircraft owners and operators. So instead of buying a replacement engine from Lycoming and Continental, they can buy an emission-free one from us. And that's kind of the goal behind that. And then, let's see. This video, hopefully these work. Yeah, so this is us having put it in for the first time and setting up the coolant system. So I mentioned before, you have to get the heat out of the fuel cell, and so the way you do that is by having a series of liquid cooling channels within the fuel cell and pumping coolant through it, and then that coolant goes into a radiator, and then the radiator then either uses a fan when you're on the ground or uses RAM airflow in flight and during taxi. So that actually turned out to be a big challenge because we didn't want to have to design our own radiator, so we had to find one that would actually fit. Let's see. This was from just before I left for Europe a couple weeks ago. I'm always the one going around with the GoPro video and things, so I'm sad that I haven't been there for the past 2 weeks to help them. And so this was actually a big moment for us. This is the first complete integration of the fuel cell with the hydrogen tanks and the electric motor. So that was our next milestone for our Air Force customer to show that we're basically ready for flight because now we can put on the propeller, right? Because you don't want to have people around when the propeller's on there. And then we can do higher ground tests at higher speeds and higher powers. Then we'll do a low-speed taxi. Then we'll do a high-speed taxi. Then we'll put on the cowling because we actually are having the students fabricate a custom cowling for us because that's what we have to do based off the way we configure the box this first time. And then we'll be able to do our first flight demonstration. So all summer we'll be doing our flight tests, and that was the next phase of the company. But I guess to summarize what I mentioned today is that I do believe that we can have green technologies to not only solve our transportations here at home, but hydrogen also works for launch vehicles. Hydrogen and electric propulsion, which is what my PhD is actually in for spacecraft, also is emission-free. It can be used to get us from places from Earth to the moon and beyond. So we do have the technology suite to connect us throughout the solar system in a green way. So we don't have to continue to burn hydrocarbons and pollute the atmosphere to be able to do what we want to do. And I think that is a powerful knowledge that I want to share. And I think that probably goes for everybody's industry, that there are ways to be a lot more efficient, a lot more green. And in terms of the future of what we're working on, we're not only interested in single-engine aircraft. That was something that was I was very passionate about because I am a very active pilot in this space, but we want to decarbonize marine. So one of the biggest polluting sectors out there is the marine sector. And fuel cell technology is an easy fit for marine applications because the vessels are so big, right? So they have a lot of space for it. So you don't even necessarily have to store your hydrogen as liquid, although you probably still want to. So that's something that we are interested in having our product go in there. The Hyperloop, I hope it happens sooner rather than later. I know you've got a company, I've met them before, Heart Hyperloop, when I was working for Virgin Hyperloop. We do think there is a potential for it going in jet aircraft, but you probably want to shift to a different membrane technology that can go higher in temperature, because as you go in higher in altitude, you need a higher air compression ratio, which generates more heat. We're also interested in Mars robotic vehicle applications, as well as human Mars exploration. And we actually have NASA Johnson, who helped us with our phase 2 Air Force proposal, because our membrane is very durable, so it works really well for human space exploration time intervals, which can last many, many years before you can do a replacement. And I think that probably is my last slide. So I wanted to, if I would appreciate if you would follow our company and our progress. We haven't released any of those GoPro videos yet. I'm going to tweak them a little bit more and then start putting them out on social media. So Hydroplane Aero is us on Twitter. I'm more of a Twitter user, but we also have Instagram, and I'll also post it to Instagram. And then my Twitter is Dr._Astro.